Bismillah ar-Rahman ar-Rahim. We are interested in the stationary or invariant distributions of an irreducible discrete-time Markov chain. Our Markov chain is irreducible. This means that all states communicate. So for every I and J, we have I leads to J and J leads to I. J is accessible or reachable from I, and I is accessible or reachable from J. This means that there exists some non-negative integer m, and there exists some non-negative integer L, such that Bij of m, the m step transition probability from I to J is strictly positive, and the L step transition probability from J to I is also strictly positive. This means that sooner or later in this Markov chain, any state can be reached from any other state. We want to prove the theorem that there exists a stationary distribution in such an irreducible discrete-time Markov chain if and only if some state is positive recurrent. We start our proof by assuming that there is some state K that is positive recurrent. So K is in the set S, the set of all possible states. Those are the values that can be taken by the discrete random variables of the Markov chain, x0, x1, x2, and so on. We will define psi k comma I, so it depends on k. K is this state that is positive recurrent. And let's initially assume that I is not equal to k. And psi ki will be the average of the number of visits starting from k to I before revisiting k. Okay, so if you have a summation n from 1 to infinity, indicator xn is equal to I, and tkk, so that's the recurrence time of state k, is greater than or equal to n. So x0 is k, we start in state k, and then we have a summation here from 1 to infinity, and we keep track of xn equal to I. We monitor whether at the time instant n, the discrete time Markov chain is in state I, or we track whether xn is equal to I. So this is a counter of the number of visits to state I, given that the chain starts in state k. But also, we want the recurrence time of state k to be greater than or equal to n. Now, if I is not equal to k, then tkk greater than or equal to n is equivalent to tkk strictly greater than n, or tkk greater than or equal to n plus 1. Because if I is not equal to k, then at the time instant n, we are sure that we are not in state k. So by putting this condition on the recurrence time of state k, we are counting the visits to state I before k is revisited. We start in k, and then we count how many times I is visited before entering into state k again. So the summation of the indicator will be a counter of such visits from k to I before revisiting k. And then when we take the expectation, we mean the average number of visits. So this is the meaning of psi k comma I. And because what we are summing here, the summand is real valued and non-negative, then by Tonelli, we can interchange the order of the expectation and infinite sum. And we can take the expectation inside, and the expectation of the indicator will be the probability of the event. So the event here is xn is equal to I, and tkk is greater than or equal to n. So tkk, this is the random variable. When it is equal to v, it means that given that you start in k, that you enter into k again for the first time after v steps. Now, given the way that this psi k comma I is defined, so it's defined by this summation here, and this is its meaning. Now, what will happen if we replace I by k? So this is like a special case. If in this expression here, we put I equal to k, then xn is equal to k. tkk greater than or equal to n. That's the time needed to enter for the first time into state k, given that x0 is equal to k. Now xn is equal to k. So these two guys are equivalent to tkk being equal to n. And so this is the sum of the probabilities tkk equals n. This is the same as the sum n from 1 to infinity, the first passage probabilities, fkk of n, starting in k, and then given that we start in k, we enter into k again for the first time in n steps. And this summation here is what is denoted fkk. And since k is a recurrent state, then this summation is 1. So this is actually one way of classifying the states of discrete time Markov chain. If this summation here is 1, then the state is recurrent, whether positive recurrent or null recurrent. If this summation is strictly less than 1, then the state is transient. In that case, there will be a strictly positive probability that you start in the state, but you never come back to the state in any finite number of steps. So this will be equal to 1. So now we have this psi k of I again. If I is not equal to k, this is its meaning, the average number of visits to state I given that the chain is initialized in state k. And we count the number of visits before revisiting k. Psi kk is exactly equal to 1. Now, let's investigate psi ki if we do a sum over I in S, which again is the state set. It's the set that contains all possible values that x0, x1, x2, and so on take. If we do this summation here, then again, since the summand is real valued and non-negative, then we can interchange the order even if the cardinality of S is infinity. So even if S is countably infinite, we can do this interchange, and then we have this summation. If we look at this sum, we are saying that xn is equal to I, and we are summing over any possible I. Well, the DTMC is in one of its states. So if we sum over I, this is exactly the probability that tkk is greater than or equal to n. And this summation, n from 1 to infinity, probability tkk greater than or equal to n, is the expected value of tkk. That's mu kk, the mean recurrence time. This is summation n from 1 to infinity k f kk of n. And since k is a positive recurrent state, not null recurrent, then this mean recurrence time is a finite number. So we need this, I mean, we will need it later, that we need this summation here is a finite number. Note that this will not be true if k is null recurrent. For a null recurrent state, the mean recurrence time is infinity. Okay. And of course, here we applied, this rule that this is if we have a random variable that takes non-negative integer values, then this is a formula for its average or its first moment. Okay, if we have a random variable, let's say z, and z is a non-negative integer, so the mean value is summation n from 0 to infinity or 1 to infinity n, probability that z is equal to n. Then we can write down this n from 1 to infinity summation. I can write it as a summation k from 1 to n of ones, then probability that z is equal to n. So here we are summing n from 1 to infinity. We are summing k from 1 to infinity, 1 times the probability that z is equal to n. So this is the expression for the expected value or the first moment of z. Now we can interchange the order. The summand here is real valued and non-negative. And so rather than summing n from 1 to infinity, k from 1 to n, we can take the summation k from 1 to infinity, and then we can sum n from k to infinity. Right? Because, so if n, this is n, and it is here 1, 2, 3, 4, 5, and here is k. Now, if n is 1, k is equal to 1. If n is 2, k goes from 1 to 2, 1 to 2 here. And if n is 3, then k is 1 or 2 or 3. If n is 4, k 1, 2, 3, 4. What we are doing is to fix k, so this will be the outer sum, and then do the summation first with respect to n. So if we fix k, then n starts from k all the way to infinity, and then we have 1 and the probability that z is equal to n. Okay. And now this summation here, we are summing the probability that z is equal to n from k to infinity. This is exactly the probability that z is greater than or equal to k. Okay, so an alternative expression for the first moment for a random variable that takes non-negative integer values, rather than using, multiplying the PMF with n and summing, we can just sum the probability that this random variable is greater than or equal to k. So we have this here, and this is indeed the mean recurrence time of the state. Given that the state k is a positive recurrent state, then this quantity is finite, and this will be useful as we will see. This is what we have. Psi k comma I is given by this expression, and if we put I equal to k, then we get 1. If we sum psi k comma I over I in big S, then we get the mean recurrence time of state k. So k is a positive recurrent state. Now let's do some manipulation of psi k comma I. Let's isolate the term corresponding to small n equal to 1, and then the summation will start from 2. Now, what is this probability? This probability is that x1 is equal to I. So the DTMC is in state I at the first time instant. And the number of steps to revisit K for the first time is greater than or equal to 1, given that x0 is equal to K. Well, the state is a recurrent state. So this event is almost sure. So this is equal to the probability that x1 is equal to I, given that x0 is equal to K. Note again, for a positive recurrent state or for a recurrent state in general, even if not recurrent, then sooner or later the state will be re-entered for the first time. And this is the definition of a recurrent state. Now, this is a transition probability, a one-step transition probability from K to I. So this is PKI. PKI is multiplied by 1. And for reasons that will become clear shortly, let's write this one as epsilon kk. So the first term here corresponding to n equal 1, we will write it as the one-step transition probability from K to I epsilon kk, which is equal to 1. Now, what about the second sum here? We will introduce this event, xn minus 1 is equal to j. So we have summation n from 2 to infinity, and then we will sum j in s, probability xn is equal to I, xn minus 1 is equal to j, tkk is greater than or equal to n, given x0 is equal to k. Now tkk, so the chain enters into state k again for the first time after a number of steps that is n or more. So if we put j here that is equal to k, then the probability is equal to 0, right? So if j equals k, because we have here tkk greater than or equal to n, the probability is 0. Okay, so there will be a term that is 0 if j is equal to k. We can just remove this term and rewrite this double sum as summation n from 2 to infinity, j in s, j not equal to k, probability xn is equal to I, xn minus 1 is equal to j, tkk is greater than or equal to n, given x0 is equal to k. Now, if at xn minus 1, the discrete time Markov chain is in state j, at time instant n, the discrete time Markov chain is in state I, okay, then because j is not equal to k, we can say that this is equal to summation n from 2 to infinity, summation j in s, j not equal to k, probability xn is equal to I, xn minus 1 is equal to j, and then tkk greater than or equal to n minus 1. Greater than or equal to n minus 1. Okay. Now, we know that at n minus 1, the chain will not enter into state k again because j is not equal to k. So this change here, given that j is not equal to k, will not change the probability. Okay. Now let's apply the chain rule for probabilities. What we'll do is we will take this and write it as probability xn is equal to I, given xn minus 1 is equal to j, tkk is greater than or equal to n minus 1, x0 is equal to k, times the probability that xn minus 1 is equal to j, tkk is greater than or equal to n minus 1, given x0 is equal to k. Let's study this. Here we have xn is equal to I, given xn minus 1 is j. So here we have xn minus 1. This is like present. This is like future. Here we have x0. And here we have the event tkk greater than or equal to n minus 1. We can know whether this event is true or false by examining the sequence from x0 to xn minus 2. If any of those guys other than x0 is equal to k, then this event is false because the chain has returned to state k for the first time in a number of steps less than n minus 1. If all those guys except x0 are not k, then this event is true. Then re-entering into state k for the first time will happen later in time. Because of this, because first passage events are stopping times, then this probability here is just by the Markov property is equal to the probability that xn is equal to I, given that xn minus 1 is equal to j. And this is the one-step transition probability from j to I. So now what we have is summation n from 2 to infinity And then we have summation j in Sj not equal to k, Bji times probability that xn minus 1 is equal to j, tkk is greater than or equal to n minus 1, given that x0 is equal to k. Now we can do the summation n from 2 to infinity of this. We can define m to be n minus 1. In this case, we will have summation j, Sj not equal to k, but then there will be summation m from 1 to infinity, probability x of m is equal to j, tkk is greater than or equal to m, given that x0 is equal to k. And this is exactly the definition of psi k comma j. And let's not forget the Bji that we have here. Splitting our summation for psi k comma I, now we can write it as two terms. So psi k comma I is equal to pki psi kk plus summation j in S, j not equal to k, pji psi k comma j. This term here is the missing term in the summation. If j is equal to k, we have pki psi kk. So this is exactly the missing term here. Now we have a nice result. Psi k comma I is equal to summation j in S, psi k j p j I. This is like collecting psi k comma j in a row vector. So here will be an element psi k comma j, and this row vector is of size 1 times the cardinality of set S. And then here we have bji, that's the transition probability matrix P, and here we have its ith column. In other words, if we collect those psi's in a row vector, then this row vector is equal to itself times the transition probability matrix P. This looks very much like an eigenequation for a left eigenvector of matrix P, the transition probability matrix. Now the question is, can we take this vector and make it a probability vector? A vector, it contains non-negative elements, okay, because of the definition of psi. Psi is the sum of probabilities, and psi kk is 1, so it contains non-negative elements. But can we make the vector such that the sum of its components is equal to 1? Yes, we can do so by taking the vector and dividing it by the sum of its elements, so that we have the normalization. And now the probabilities in the vector are like a PMF. And this is feasible because the sum of the elements in this vector is summation psi kj, where j is in S. And previously, we have shown that this summation is exactly the mean recurrence time of a state k. And because state k is positive recurrent, then this mean recurrence time is finite. So if we define psi tilde of ki as psi of ki divided by the sum, which is psi ki divided by mu kk, then we have a stationary distribution. We have an invariant distribution. We assumed that there is some state k that is positive recurrent, and by an actual construction, we obtained what can possibly be a stationary or invariant distribution for the discrete time Markov chain. Now that we have a stationary distribution, then note pi is equal to pi p. If we multiply both sides from the right by the transition probability matrix P, then pi p is equal to pi p squared, but this is equal to pi. So pi is equal also to pi p squared, and so on. So pi is equal to pi p to the power n for a non-negative integer n. So this means that we also have these expressions. We have psi k comma I is equal to the sum, and we can replace bji from the previous page by bjin. So that's the n-step transition probability from I to j. You know, this is basically element ji in the matrix P to the power n. And if we divide both sides by mu kk, which is the mean recurrence time of the positive recurrent state k, then we get this expression for psi tilde. Recall that our interest is in a chain that is irreducible. Okay, so if we take state I and state k, then they communicate. I leads to k and k leads to I. This means that there are non-negative integers m and l, such that bik of m, that's the m-step transition probability from I to k, and bki of l, which is the l-step transition probability from k to I. Both these probabilities are strictly positive. And we must be able to find those M and L given the definition of an irreducible DTMC. Epsilon k comma I is summation j over s epsilon k comma j bji of L. That's the L step transition probability from j to I. That's the probability that xl is equal to I given that x0 is equal to j. Now this is element ji in the transition probability matrix raised to the power n. And we know that this expression is true because it's true for any n here. We just use L. Why L? Because we know that pki of L, that's the L step transition probability from k to I, is strictly positive. We have a strictly positive probability to go from k to I in L steps. Here we have a summation, and this is a summation in which the terms are non-negative. And so we can lower bound this sum by one of the terms. And we will choose to lower bound this sum by the term in which j is equal to k. So this summation kj in S, epsilon kj bji of L is greater than or equal to, we will put j equal to k, epsilon kk bji of L. Now epsilon kk is equal to 1, and this probability is positive, and so epsilon ki is greater than or equal to pki of L. Now let's write this expression replacing I by k. So we have epsilon kk, which is equal to 1, is given by this summation. Again, a sum with non-negative terms, so it is greater than or equal to one of the terms, and we will choose to set j equal to I. Then 1 is greater than or equal to epsilon k comma I, and then we have bik of m. This is choice of m such that this probability is positive. And so 1 is greater than or equal to epsilon k comma I bik of m. So using these, we can have a bound on epsilon ki. So see here, the impact of the chain being irreducible is that those guys here are guaranteed to be strictly positive. And in fact, we can also put a bound, an upper bound on them. Okay, so epsilon ki is positive for every I in S. Let's repeat this part, because it's this part that requires that the chain is irreducible. Note that I took an element I in the set big S, the set of states. And I said, well, I and K, this positive recurrent state, they communicate. Regardless of I know that they communicate because our interest is in a discrete time Markov chain that is irreducible. Every state communicates with every other state. Every state is reachable from every other state. And because I leads to K and K leads to I, then we are sure that we can find these two strictly positive probabilities for some positive integer m and positive integer L. We are sure about this. Then we used basically the expressions which come from the eigen equation for the transition probability matrix raised to some power. And now we have that epsilon k comma I can be lower bounded by something that is strictly positive and can also be upper bounded. Epsilon ki is always positive in the situation when the discrete time Markov chain is irreducible. Recall that on the first page, our theorem was an if and only if statement. So we have an irreducible discrete time Markov chain, and we said that there is a stationary or invariant distribution if and only if there is a positive recurrent state. So the first part was, suppose that there is this state k that is positive recurrent. And using this epsilon function, we were able to obtain a stationary distribution. Now it's time to assume that there is a stationary distribution and try to conclude that there must be one state that is positive recurrent. We now assume that there is a stationary distribution. Suppose that it is in this row vector pi, and pi is equal to pi p, and this will lead to pi is equal to pi p to the power n, and p again is the transition probability matrix of the discrete time Markov chain. Now this is a distribution, so it must be the case that if you sum the elements, you should get unity. And because the guys are non-negative, then one of them, at least one of them, must be strictly positive. So we have the pi's, the elements of this vector, the invariant distribution, they sum to 1 and they are non-negative. So one of them, let's say by V, is strictly positive. Now take another state, gamma. And because the chain is irreducible, so every state is accessible from every other state, then there must be M such that PV gamma, note that V is this state, we are sure that by sub V is strictly positive, PV gamma of M is strictly positive, which means that take some state gamma, some other state gamma, and there is a positive integer M such that the M step transition probability from V to gamma is strictly positive. we are sure that such M exists because we are talking about an irreducible discrete time Markov chain. Write an expression for pi of gamma. From here, we know that pi of gamma is equal to summation J in S by J bj gamma of M, sum of non-negative terms, so we can lower bound by one of the terms. We will choose J to be equal to V. This will be our lower bound by V bv gamma M. Now this is strictly positive, and this is strictly positive. So pi gamma is strictly positive. So we start by assuming that there is a stationary distribution for this irreducible discrete time Markov chain, because the stationary distribution in this row vector here must sum to unity, and the probabilities are non-negative, then we are sure that at least one element, one probability must be strictly positive. Then we used the irreducibility of the chain to show that this indeed means that every component in the stationary distribution will be strictly positive. This is our conclusion. All components of pi, the invariant distribution, are strictly positive. Now take pi v. It's a number. It's a positive number. Take the limit as n goes to infinity. So this is like a constant sequence with respect to n. And so the limit is this pi v itself. But write down an expression for pi v using pi is equal to pi p. So this is a summation j in S by j bjv, and then we have of n. Remember that this leads to pi is equal to pi, and then we can raise the transition probability matrix to any positive integer. Now let's look here. We want to take the limit. Where is n? N is in the n-step transition probability. It is inside the sum. And perhaps our discrete time Markov chain has a countably infinite number of states. So it may not be possible to interchange the infinite sum and the limit. But in our case here, this is justified. And the reason is that this is the summand. The summand depends on j, the index of summation, and this n. Can we upper bound the magnitude of the summand by a quantity that depends only on j and not on the variable with respect to which we are taking the limit? Yes, because this probability can be upper bounded by 1. And so an upper bound on the magnitude of the summand is by j. And what about the sum of by j over j? Well, that's unity. And so the sum is finite. Then we can employ the dominated convergence theorem, because we can upper bound this by an upper bound that is summable and that does not depend on the variable with respect to which we are taking the limit. Then by the DCT, the dominated convergence theorem, we can take the limit inside, like this. Now suppose that the states of the Markov chain are all transient or non-recurrent, or a mixture of transient and non-recurrent. In other words, suppose that there is no positive recurrent state. In this case, we know that the limit will be 0. And so the sum will be 0. And so pi v will be 0. But this contradicts the fact that if we have an irreducible discrete time Markov chain and it has a stationary distribution, then all the probabilities must be strictly positive. Because of this, we know that at least one of the states must be positive recurrent. There is at least one positive recurrent state. And because all states communicate, then all the states will be positive recurrent. Now we show that the stationary probability by j for state j is 1 over mu jj. So it is the reciprocal of the mean recurrence time, and that's it. We are talking about a unique stationary distribution. Consider a chain that is initialized by a stationary distribution by j. Let's investigate mu jj by j. Because the chain is initialized by the stationary distribution, then the probability that xn is equal to j is equal to by j for every n greater than or equal to 0. Now, write down the expression for mu jj. So this is summation n from 1 to infinity, probability that tjj is greater than or equal to n. Tjj is this random variable telling us the number of steps needed to go from j and enter into j again for the first time. Probability tjj greater than or equal to n, given that x0 is equal to j. And this is multiplied by j, which is the probability that x0 is equal to j. Let's combine these two probabilities as summation n from 1 to infinity, probability that tjj greater than or equal to n and x0 is equal to j. The next step, let's isolate from this summation the term that n is equal to 1. So we'll take this term, n equals 1, and then the sum will start from 2. Now the state j is a positive recurrent state, and so this joint probability is simply the probability that x0 is equal to j, which is by j. Now let's focus on this event here. This event tells you, starting from j, you will not come back to j except after any steps or move. And so this probability is exactly equal to the probability that x0 is equal to j, but x1 not equal to j, x2 not equal to j, all the way to xn minus 1 not equal to j. Later, you can enter into state j, no problem, but we must have tjj greater than or equal to n. What if we take this probability and add to it the probability that x0 is not equal to j, x1 is not equal to j, x2 is not equal to j, and xn minus 1 is not equal to j? If we sum these two probabilities, here we have x0 is equal to j, here x0 is not equal to j, the sum will be the probability that x1 is not equal to j, x2 is not equal to j, and xn minus 1 is not equal to j. So what we will do is we will take this probability and write it as this probability minus this one. Right here. So ujj pi j is probability x0 is equal to j, which is by j, and then we have this sum, n from 2 to infinity, and then we have this minus that. Now we will manipulate this probability here. This is the probability that x1 is not j, x2 is not j, all the way to xn minus 1 is not j. I can write down this joint probability as a summation with indices I1 all the way to in minus 1. Every index can take any value from the set big S except j, because the events of interest are that x1 is not j, x2 is not j, and so forth. Now take this joint probability and use the chain rule for Markov chains. So this probability is probability that x1 is equal to I1 times the probability that x2 is equal to I2, given that x1 is equal to I1, times the probability that x3 is equal to I3, given that x2 is equal to I2. And we will continue doing this in probability xn minus 1 is equal to in minus 1, given xn minus 2 is equal to in minus 2. Now, what is this probability? Probability that x1 is equal to I1. Now, this is the probability that x0 is equal to I1. So this is probability that x0 is equal to I1 or xn. Remember that this is a chain that is initialized by the stationary or a stationary distribution. And so the PMF of xn does not depend on n. At any time instant, xn will have the same probability mass function. And so I can take this probability x1 is equal to I1, and I can write it as the probability that x0 is equal to I1. Now here we have, this is in one step, we make a transition from state I1 to I2. So given that at x1, we are in state I1, what is the probability that at time instant 2, x2 is equal to I2? And all the guys are one-step transition probabilities. Now, our discrete time Markov chain is homogeneous. And because it is homogeneous, then the transition probabilities will depend on time differences, not on absolute times. So this transition probability can be written as probability x1 is equal to I2, given x0 is equal to I1. This probability can be written as probability of x2 is equal to I3, given that x1 is equal to I2. Now I can take those probabilities and write them as a joint probability. The probability that x0 is equal to I1, x1 is equal to I2, x2 is equal to I3, all the way to xn minus 2 equal to in minus 1. Like this. And what is this probability? Note that we are summing over those indices, and they can take any possible value in the set big S except j. So this summation here yields the probability that x0 is not equal to j, x1 is not equal to j, all the way to xn minus 2 is not equal to j. Let's recap what we did. We took mu jj by j, and this is probability n from 1 to infinity, probability that tjj is greater than or equal to n, given that x0 is equal to j, and this pi j is the probability that x0 is equal to j. We joined these two guys as the probability that tjj is greater than or equal to n and x0 is equal to j. Then we split the summation. We isolated the term n is equal to 1, and this gave us probability that x0 is equal to j. Now the sum, starting from 2 to infinity, is the probability that x0 is equal to j and tjj is greater than or equal to n. Well, we can write down this as probability that x0 is equal to j and then x1 is not equal to j, all the way to xn minus 1 is not equal to j. And then we wrote this probability as a difference. And this difference is that this probability is probability that x1 is not equal to j, x2 is not equal to j, xn minus 1 is not equal to j, minus the probability that x0 is not equal to j, x1 is not equal to j, xn minus 1 is not equal to j. Then using the properties of the Markov chain is homogeneous, and we have the Markov property. This probability here is exactly the probability that x0 is not equal to j, x1 is not equal to j, all the way to xn minus 2 is not equal to j. So now this is the difference that we have, and it is an interesting difference. Note that here we have x0 is not equal to j, all the way to xn minus 2 is not equal to j. Here we have the same thing, but we have one extra. xn minus 1 is not equal to j. And as we can see, we have now a telescopic sum. We can write the infinite sum as limit big K tends to infinity, summation n from 2 to k, and then this is the sum. And as I said, we have a telescopic sum. So when n is equal to 2, we have probability that x0 is not equal to j, minus the probability that x0 is not equal to j and x1 is not equal to j. If n is equal to 3, then we have plus the probability that x0 is not equal to j, x1 is not equal to j, minus the probability that x0 is not equal to j, x1 is not equal to j, x2 is not equal to j. If n is equal to 4, we have the probability that x0 is not equal to j, x1 is not equal to j, x2 is not equal to j, minus the probability that x0 is not equal to j, x1 not equal to j, x2 not equal to j, x3 not equal to j. And as we can see, and so on, and we are left with two terms. So we'll have probability that x0 is not equal to j, which can be combined with this guy to give unity. And then we will have the very last term, which is minus, and then this probability with small n equal to big K. This is what we have. These two guys, they sum to unity, and then we have this limit, as k tends to infinity. By the continuity of probability, this is the probability of the intersection v from 0 to infinity, xv is not equal to j. Now let's think about this probability. This probability is the probability that state j is never visited at any time instant whatsoever. But note that we have an irreducible discrete time Markov chain. Note that all states communicate and all of them are positive recurrent. So even if we start in a state that is not state j, we will need to visit state j sooner or later. In fact, we need to visit state j infinitely often. So this probability here, given that we have an irreducible discrete time Markov chain in which all states are positive recurrent, is equal to 0. And so mu jj pi j is 1, and the stationary probability by j is 1 over the mean recurrence time of state j mu jj.